My name is Nate Slater. I'm a senior manager of solution architecture at AWS. I lead a team of solution architects out of the San Francisco Bay Area. And today we're going to be talking about migrating from relational database management systems to NoSQL. And we're going to also have a real-world customer use case of a migration that Sony performed. And we have Ben Anaki from Sony who will be describing that process. But before we talk about Sony's migration, let's jump in and talk a little bit about what we're going to learn in today's session. So first we'll go through some of the key differences between NoSQL database and an RDBMS. Just a show of hands, how many folks in the room are either familiar with NoSQL or are using a NoSQL database? Okay, great. So we've got most of the room is familiar with NoSQL. We'll learn some of the fundamentals of Amazon DynamoDB. So same thing, how many folks here actually use Amazon DynamoDB? Okay, probably about a third it looks like. So for the folks that are new to Dynamo, we'll review some of the key concepts just so you have an idea of what you're going to be faced with if you do a migration from RDBMS to NoSQL. We'll talk about use cases, right? You don't want to take a transactional entity-based system in RDBMS and move it wholesale into Dynamo, right? The point of this presentation is to talk about the suitable use cases, right? And there are definitely some where Dynamo is really going to be a great choice. We'll talk a little bit about how you'll plan and execute a migration, right? So like anything else, it's a process. There's a number of steps you'll need to take in order to be successful. And then at the end, we'll explore the customer use case. So year 2016, I don't know if folks probably have seen versions of this slide. I've seen it going back to probably 2014. It's the big data landscape slide, and if you look at this, it's just unbelievable how many choices there are. It's really daunting, the number of choices that you have today when you talk about data storage and analytics. The good news is, though, that there really are many, many choices. It's great that customers have that many choices in the marketplace, but at the end of the day, you don't really ever need to consider even a fraction of those, right? The RDBMS is the workhorse. Even though we have a lot of new different types of databases, document databases, NoSQL databases, key value stores, in-memory databases, it's still the workhorse, right? We see pretty much most customers, even if they are running other types of database systems, will have a RDBMS someplace in their stack. And then we have NoSQL, right? This is the relative newcomer. NoSQL really burst onto the scene probably 2007, 2008 was when you really started hearing about it. 2007 was when Amazon published the Dynamo paper. And then in 2008, you started to see systems like HBase and some of the other distributed databases that sit on top of the Hadoop frameworks. So been around for a while, and the key with NoSQL is that it's really optimized for high volume, high velocity data. So if you're dealing with thousands and thousands of concurrent transactions and a stream of data that's high velocity, continuous, NoSQL works very well. So why does it work well, right? What makes NoSQL so good for these types of workloads? Well, first it has horizontal scaling. So what that means is that instead of scaling out an individual box or server, you actually add more servers. And that allows massive scale at an affordable price. It has high concurrency. So one of the things about a NoSQL system is that they're not ACID compliant. So it throws away some of the consistency and isolation guarantees that you get with a relational database in order to allow higher concurrency because you don't have to lock tables and lock rows in the same way that you do with a relational database. And it has a flexible schema. So DynamoDB is basically a key value store, or you can store JSON documents. And what's interesting is that each item in the table doesn't need to have the same attributes, right? You can have items in the same table that are completely different in the attributes that they have. You can do this, of course, in a relational database, but what that means is you end up with columns with lots of null values in them, so you have very sparse data, which is also not efficient. So scale up, that's a term that we'll be using throughout the talk today. Scale up basically is vertical scaling. What that means is that you're going to replace your existing single server or maybe a redundant array of servers with bigger, faster, more powerful hardware. And what this means is that costs go up very, very quickly. The trade-off is that you have lower operational complexity. You're simply running the same database that you were previously running, just on a more powerful box. But at the high end, everything is proprietary, down to the types of memory that you're going to run, right? So it can be very, very expensive. And you're going to reach a point where you're on the biggest, fastest box that money can buy. And if that's still not enough, what do you do? Well, the solution is you're going to scale out, right? You're going to basically use commodity hardware, and you're going to just run lots and lots of copies of that hardware. But it can be a little bit operationally complex. With databases, really, that comes down to two things. Sharding, which is essentially partitioning your data by key space, and then replication, right? When you have your data distributed across different nodes of a cluster, you don't want the failure of any given node to result in a loss of data. So what that means is you have to manage copying data across nodes. It seems simple on the surface, but it's actually very complex because what happens if you make a copy and the node doesn't acknowledge that the copy was made, right? You have all of these sort of consistency and consensus issues that you need to deal with, and in distributed computing, those are actually very challenging problems to solve. So Amazon DynamoDB, good news is that DynamoDB hides all that operational complexity for you. You still get all of the advantages of a fully managed, horizontally scaling system, but you don't have to manage any infrastructure. The scaling is handled transparently by the service itself. So as you need more I/O, you can request it, and we scale it out for you. And it's ideal for highly concurrent reads and writes of small items. And small is the key word here. We do have a limit on item size in Dynamo. I believe today it's 400K. You'll find that if you do the math, if you're reading and writing really large items in Dynamo, the costs go up pretty significantly simply because you have to use more IOPS per read and write. But when you're dealing with small items, it's very, very efficient. So some of the suitable workloads for Dynamo, and these are things that we see customers running today. Ad tech is a very, very common use case. Obviously, when a user's request comes in from a mobile app or a browser, an ad tech company oftentimes needs to take the cookie information and determine what ads they should serve back to the app or to the browser. That needs to be a very low latency operation. Typically, ad tech companies have latency guarantees of maybe 200 milliseconds or less. Otherwise, the performance of the app degrades. And in the web world, that can cause a lot of bad things with search engine optimization and other things. So ad tech, a very, very common use case for NoSQL and for DynamoDB. Mobile applications, right? Mobile application, it's really one of scale. If you write a mobile application and it takes off, you could go from having a very small number of users to a very, very large number of users very, very quickly, right? Hundreds of thousands of users, right? Anybody who has a mobile device could potentially be running your app. So you need that high concurrency there. And it's a great place. Dynamo is a great place for session data, right? So you can store information about the user's session. We see a lot of Dynamo usage in gaming. And I believe the folks from Sony are going to actually be talking about a gaming use case. Again, games, whether you're on a network of console-based games or mobile-based games, you need high concurrency, you need low latency. You're oftentimes dealing with unstructured data, and so Dynamo is really going to shine there. Large-scale websites, session state, user data for personalization, access control. When Amazon wrote the original Dynamo paper, I believe one of the use cases was the shopping cart, right? They realized that storing the shopping cart in a big relational database is just simply not efficient. You don't need full consistency with a shopping cart. It's not the end of the world if someone puts an item in the shopping cart and then refreshes the page and the item's not there. What are they going to do? They just add the item back, right? But if the database is locked down and you can't actually put items in the shopping cart to buy something, they're going to leave the site. And so that was something that was one of the motivating factors behind Amazon's original paper about the Dynamo architecture. And then nowadays, we see a lot of Internet of Things use cases as well, right? When you have, it's sort of similar to the mobile use case, you can have potentially, thousands, tens of thousands of mobile clients or IoT sensors rather, that are sending data into Dynamo, oftentimes as a stream. Okay, so let's jump into some of the fundamentals here. We'll go pretty quickly through these. I definitely encourage folks who haven't used Dynamo to really take a look at it, but these concepts should become clear once you've had the chance to play with the service. So the first thing you need to understand with Dynamo is the key. that you're going to use on your table, right? The table is the sort of topmost entity in Dynamo. You don't create a database and then add tables to a database. You basically just create tables, and the tables live in the region of the account that you're using with AWS. So when you create a table, you have to define a partition key. This is mandatory. A partition key is ultimately going to tell Dynamo how it's going to distribute your data across the nodes of the cluster of compute that's running the DynamoDB. And there's some very important characteristics of a partition key that you need to be aware of in order to get an efficient use of Dynamo. You can optionally add a sort key as well. So a sort key is essentially going to be a set of records within a specific partition key space that are sorted on disk. You can think of this almost like a one-to-many relationship, right? So you have the partition key, which is the one side, and then the sort key, which is the many. You could think of maybe a device ID and a timestamp field, right? That would be a partition key and a sort key combination on the table. Because the data is sorted, it allows you to do lexicographical operations, right? So you can do things like greater than, you can do range queries. So it's a very powerful way to actually query data out of Dynamo. And then we use the term primary key to define just what uniquely identifies the item in the table. So in the case of a table that just has a partition key, the partition key is also the primary key. What that means is that every item in the table is going to be uniquely identified by its partition key. If you have the partition key sort key combination on a table, then it's the combination of those two values that uniquely identify the item. So that would be the primary key. So you have something called a local secondary index. So let's say you had a partition key and a sort key, and you defined that on the table when you created it, but you also have another attribute in your table that you want to treat as an alternative sort key. What you would do is, since a table can only have one primary key, right? What you do is you create a local secondary index, which would have the same partition key as the table, but a different sort key. You can also create something called a global secondary index. A global secondary index can be basically a version of the table that has a different partition key, and it can be a version of the table that has a different partition key and sort key. So really anything you can do with an LSI, you can also do with a GSI. There are some differences. The LSIs are stored on the same partition as the table itself, and so we impose a size restriction. So if, I think it's 10 gigabytes. And so what that means is that if you feel like your index is going to get bigger than 10 gigabytes, you need to switch to a global secondary index. Global secondary indexes are maintained automatically. They're updated asynchronously. So when you update an item in Dynamo, the Dynamo service will update the index. But you don't have to do anything special. It happens for you. Now, what that means, of course, though, is that a global secondary index can only be eventually consistent, right? Because there's going to be a window of time, small one, but a window nonetheless where a change to the primary table may not yet be seen in the GSI. Ultimately, I tell people, unless you need full consistency, use a GSI. It's just going to be easier. You can add them after the table's created. There's no size restriction, and you can do everything with a GSI that you can do with an LSI. A query is basically an expression that you pass into the Dynamo service that will return pages of items from a table or an index. So when you run a query in Dynamo, you have to tell it which table or index you're going to use. And then you have to supply the primary key, and if it's an index or a table that has a sort key as well, you provide the sort key, and then the operation that you want to perform. And Dynamo then will return 0 or more records back to you. It returns records in pages. Pages are 1 megabyte in size, so if you get more than 1 meg worth of items, you have to page through the result set. Okay, so partition. This is basically a shard of data. So your table is actually sharded automatically by the Dynamo service. And this is where the partition key becomes really, really important. The way that Dynamo is going to partition your table is based on taking a hash value of your partition key. And so what this means is that if you want your data, ultimately you want your data to be uniformly distributed across as many partitions as possible. If you pick a partition key where you have a frequency distribution of values where certain values are in much higher frequency than others, you're not going to get a uniform distribution of data. And this can cause some unpleasantness when you go to read and write data from the table, because what that means is that reads and writes are localized to a partition or set of partitions rather than across all the partitions of the table. The number of partitions that you have in your table is determined by taking the maximum of the partitions required for storage. So if you think your table is going to be 100 gigabytes in size, today each partition is 10 gigs. You would divide 10 into 100 and you'd get 10. So your max there would be 10 partitions just for storage. Then you have to look at the amount of I/O you need. Each partition today, I think, can deliver 1,000 write IOPS and 3,000 read IOPS. So you would have to take the number of read IOPS that you want on the table, divide it by 3, take the ceiling of that, and then add that to the number of write IOPS divided by 1,000, take the ceiling of that, add those two numbers together, and then you take the max between the number of partitions for storage and the number of partitions for I/O, and that's the number of partitions you can expect to have with Dynamo. So this is some of the type of things you'll need to be aware of when you're planning your migration from your RDBMS is really what number of partitions are you looking at, and what is going to be the best key structure for your tables. Okay, so the migration process. This state diagram shows basically, you start with the planning state, then you go to the data analysis state. Data analysis, you go to data modeling. There's probably some iteration within that state, right? It's unlikely you're going to get the data model right the first time. Anybody who's ever done entity relationship modeling with a relational database will tell you, yeah, you go back and forth a little bit. You're probably not going to nail it the first time. You'll need to do testing, right? And testing with a migration, oftentimes involves looking at, the results of the migration and comparing it to the original and making sure that, you got all the rows you expected and that they're in the form that they're supposed to be. And then once you're convinced that the process works and you've scripted it out and you can run it in your test environment without errors, you'll go ahead and you'll do the migration on the production database. So in the planning phase, you want to define the goals of the migration, identify the tables that are going to migrate, document any per table challenges, right? This is things like, do you have encrypted column values that would need to be unencrypted before migrating to Dynamo, or maybe unencrypted and then re-encrypted using a different key in Dynamo? There's the sort of table-specific characteristics you'll want to look at. And then, as always, you need to define and document your backup and restore strategies, right? If you do a migration and something goes south, you got to be able to recover. So some of the things that you would want to look at when you're trying to choose which tables to migrate would be entity attribute value tables. I think these are also called Model 2 tables, maybe. It's when you have a key value that's being represented in a relational database. Usually what that means is you have a table that's storing all the possible key values, a table that's storing the values, the values themselves, and then an intersection table that maps those keys with the values. Those are really, really ugly queries to write in a relational database because they're basically joins into a single union or an intersection table, and then sometimes there may even be a recursive table join you need to do. So not a happy query to write. Application session state tables, these are really easy to move to Dynamo. In fact, there are many web frameworks today that actually allow you to use Dynamo as like the backing store for storing state. User preference tables, these are good to move because oftentimes user preferences are also schemaless. Right, a user may have some set of preferences, but not all users are going to have the same set of preferences, and so relational database is a little bit of an expensive way to store that data. Logging tables are great because again, log data is semi-structured. It's not fully structured. It's also immutable. So essentially, what that means is you're going to write the record once into Dynamo, and you're never going to change it. So you don't have to worry about updates or anything like that. Okay, so backup and migration. If the migration strategy requires a full cutover, then make sure you need to you document the restore and rollback process. No surprise there. If you can, it's great to run the it's basically if you can run both systems in parallel, where you're essentially running your old system and your new system. That makes the migration a lot less risky. And if I recall from Sony's slides, that's exactly what they did. So data analysis is where you're going to look into your source tables and figure out what they need to look at or look like in Dynamo. So if your access pattern of your application is write-only or fetches by distinct value or queries across a range of value, no surprise there, you can use a combination of partition keys and sort keys in your Dynamo table. And so looking for things like one-to-many relationships, that's usually a pretty good indicator that you might have a partition key, sort key structure in the target table. You'll also want to get a sense of what your costs are going to be. So we charge by the read capacity unit and write capacity unit in Dynamo. A write is 1K in size, a read is 4K in size, and so you'll need to understand, given your access patterns, how much write capacity do I need, how much read capacity do I need, and what is this going to cost me. You can run this through the simple monthly calculator and get a number. Key structure, again, very important. You'll want to pick a good key. You want a key that gives you uniform distribution of data, and you want a key that is something meaningful. Like, for instance, if you have a user table in a relational database and you have some numeric key, you could make the numeric key the lookup or the partition key in Dynamo. It would give you uniform distribution of data, but the problem is that most of the time you might want to look up by the user's email address, not the numeric key. And remember, you don't have a query language like SQL with Dynamo, so you might want to make that email address the key. For write-only data, then you can pick just like a random UUID, right? If you're never going to go back and read that row back out, or if you do read it out, you're reading it out off an index. You're never going to do an atomic update on an individual item, use a UUID. Any RDBMS table that has a unique index on 2 key values, that's a good candidate for a partition key plus a sort key. Okay, so here's just a quick data analysis and modeling example. On the left-hand side, left-hand side, you've got the RDBMS. This is something where we might have an event, we have an order, and we have an order processing event. So maybe we're building a system that processes orders, and during the order processing workflow, we have a number of events that are generated. And so we have a table that maps orders to events, and the time that it occurred, and the payload of the event. In Dynamo, we would actually denormalize this. We're going to have a single table where we're going to have the order number, the event date, the event type, and the data, right? You can see in the RDBMS, we have an event type table. That's a normalized lookup into the order processing event. You don't want to do joins in Dynamo, right? Dynamo itself does not support joins, and you certainly want to avoid joining data sets in your application code if you can avoid it. So, this slide here is really showing, if you have a really, really large table in your relational database and you want to get an understanding of how big your items need to be in Dynamo, you can actually sample from that table, rather than try and query the entire table and add up and then take an average item size. I would recommend doing a sampling just so that it's a little bit more efficient. Maybe running that query is just impossible because the table's too big. If you pick the 90th percentile, you're probably pretty good, right? So if your items are going to be 6.6 KB and there's only 5% of items that'll be bigger than that, you can use that. And in this case, we're just walking through essentially some basic arithmetic showing, what's the number of write units we need per item, the number of read units. We know that we're going to need to do 1,000 events per 500 orders per day, so that's a total of 500,000 orders per day, or events per day, rather. Then we're going to divide that by the number of seconds in the day. That's the number of events per second. And then we're going to figure out how much write capacity we need to write that. Now, of course, this assumes that the activity is uniformly distributed across the entire day. It might not be, right? If you know that you're going to have most of your activity in a 12-hour period, then that divisor of 86,400, which is 24 hours worth of seconds, will be 12 hours instead, right? You can get the idea of what's going on here. So we know we have, the 5.78 events per second, and we have 3,600 seconds per hour. So that means we're getting 20,808 events per hour at a size of 6.6 KB. In order to read an hour's worth of events, which we apparently need to do for an ETL job, we would need to be able to read 134 megabytes per hour from Dynamo. And so now that we know basically, our write throughput and our read throughput, we can actually compute what we would need here. And in this case, we need 256 read units for both the table and any GSIs that we're putting on there, and 41 write units. Okay, testing phase. So just like anything else, doing a data migration involves testing. Testing is really not that much different than what you're going to do in any application, any software application. You're going to have basic acceptance tests, right? You need to be able to run just a subset of your test every time you do a phase of the migration to make sure that things seem like they're working. You'll have some functional tests. These are tests that are actually going to test the migration code itself. It's making sure the test can handle error conditions and can basically handle a big thing with functional test is do you have how fast can you read data from disk, right? Can you get the throughput that you need on the source table to do the migration. You'll have some non-functional tests as well. Those are testing maybe more error conditions, boundary conditions, and then you'll have some user acceptance tests. So you'll do all your testing. You'll probably run through it a number of times. I've done some big migrations of database systems in the past, and yeah, typically I would know it's ready to go if I can run my script basically end to end, and it sort of gives me reliable results every time. Once you're ready to do that, you can go ahead and plan the migration. Again, if you can do it in a way where you can migrate data from the source system into Dynamo, but keep the source system live for some length of time, some burn-in period while you make sure that the new system is working well, it really, really limits the risk of the migration. So if you can do that, I highly recommend it. If you've got to do a big bang cutover, you can do that as well. Just realize you better be darn sure that your migration process is bulletproof, because you're going to have a cutover period. Even with a rollback, things can get very, very tricky, especially with high velocity data. It's amazing, just a couple of minutes and things can get out of sync, and you can have some big problems. So in conclusion, keys to success: first and foremost, make sure you're moving the right workloads to Dynamo. Again, don't try and move a highly transactional system where you've got lots of relationships between entities into Dynamo. At least don't try and move it as in that form into Dynamo. You're not going to succeed if you do that. You got to understand your source data access pattern, right? That's a key thing here. Dynamo does not provide a generic query language like SQL, right? If you don't understand how your application is going to access your data, you're going to quickly run into problems where you realize, hey, wait a minute, I've got to actually I got to fetch items by this attribute. You could do some things with GSIs and LSIs, but you'll find it's very limited compared to what you're used to with an RDBMS. Test thoroughly and often, right? As you're doing your migration, you should be continually testing steps, run the migration lots of times, run it on subsets of data, run it on large sets of data. You really want to make sure you understand how the migration is going to work. And then, of course, like anything else, make it iterative, right? Don't just do tons and tons of planning and then expect to get it right the first time. Okay, and with that, I will turn it over to our friends from Sony.
Thank you, Nate. My name is Aki Kusumoto from Sony Interactive Entertainment. So today we'd like to take this opportunity to share how we migrated our system from the on-premise to the AWS, which is a cloud service. So we are working on PlayStation Network, which is a gaming platform to provide our network services to various PlayStation devices, such as a PS3 or PS4 and the PS Vita and other many devices. So PSN consists of various features or services, such as the PlayStation Store or online multi-game playing, and also social networking features and the community user-to-user messaging or communication, voice chat. We have many services. Then also we are running many microservices to provide such experiences. So we are constantly introducing new services or new features, but also we are dealing with some legacy issues we are having because PSN is now 10 years old. So today we will walk through how we resolve that legacy issue, then trying to keep our platform fresh. So before jumping into the detail migration architecture pattern, so let me try to share our key architecture principles. First one, always on. So which is very obvious, but also this is very important principle for us. Even the Ben will be talking about how we migrated our MySQL database to the Dynamo. But this always on, which means that no downtime migration was one big the requirement. Then the scalability, this is also the obvious, but also this was the biggest reason why we migrated our system to the AWS. AWS is having a much better scalability than the on-premise. So testability, everything should be testable. Yeah. Then backward compatibility. This is a unique requirement, a unique philosophy to us because we are running on the more online gaming business. So some, not online, sorry, the console gaming business. Then the console gaming is requiring the much strict memory control and sometimes, requiring the CPU usage. So we need really careful about changing the server-side behavior or response so that we don't we cannot break any customer experience or gaming experience. So, because it would be impacting the customer as well as some, our key partners such as, the big game publisher or small game publishers. So then last one is the common pattern. So we are trying to keep the variation, the architecture pattern or migration pattern small so that we can take advantage or we can leverage the learning from the previous disaster or previous failure or previous project. So we used to be, doing more, how can I say, taking more not random, but freedom approach to pick, A technologies. But, that was making us hard to address such a legacy issue or migrate some, older system to the new infrastructure such as AWS, because each system was having a unique issues. Then, we cannot spend our energy to troubleshoot for each services. So those are our key principles, our strategy we took for the new architecture and the data migrations. So let me pass over to Ben, who is our key system architect in our group.
Thank you, Aki. So I'll be introducing two core PSN systems that we migrated from on-premise to DynamoDB. So the first one is Friends. So how many people in this room own a PlayStation device? Quick show of hands. Nice. So PS Friends, it's the core system for social interaction. So for those who have been to other PlayStation sessions this week, I believe Alex and Dustin introduced the Friend Finder feature, how to locate new friends. It drives a lot of interaction on the console. It drives also the activity feed. So with that, Friends being a core system, it has a lot of subsystems, but it also has a lot of read access. It's a mainly read-heavy system, and it needs to support multiple platforms. So PlayStation 4 being our latest platform, PlayStation 3, Vita, PSP. We're on iOS and Android, and recently we started on PC Web as well. So I'm going to show you the original architecture that we have. It's a classical data center application. It's on-premises, it's MySQL, master-slave, sharded, and the app servers are running behind an L4 load balancer. Because it's sharded, it doesn't really scale. It's fixed sharding, and fixed sharding means that if you need to scale, you need to move data, and that means downtime. So when PS4 came along and we saw a huge increase in access, what we did is we introduced a hybrid architecture. It's a little bit of a quick fix to support more access, but what we did is we used AWS to front load our access to the data center to protect our apps in the data center. So whenever now users would look at the friends, what would actually happen is we would be serving those friends out of a cache in AWS. And whenever you add a friend, we would clear the cache, and on the next access, we would refetch it. But as you can see in the previous architecture, it's quite complicated. It has a lot of failure points. You need to monitor everything, and it's overall complex. So what we did is we said we don't want to operate it. We're going to move completely to the cloud. And you can see, compared to the previous slide, it's a lot more simple. So it's Amazon Route 53 with an ELB, Amazon EC2 instances, which run our apps, DynamoDB for the storage, and then Elasticache, just as previously. So the primary key is the user A, and the Second key is user B or C, and the relationship is stored with that. So in this case, user A and B are friends, and user A and C are requesting friendship. Well, A is requesting C to become their friend. So DynamoDB's data model is very suited for storing those kind of relationship data. So the core part about it was, as Aki mentioned before, is always on was one of our core principles. We can't go down. So what we did is we looked at different approaches of how we can avoid downtime during our data migration and rollout. And what we did is we already had the SNS in place from our data center. So we attached an SQS to it and started buffering all the writes to the database in that SQS. And then once the writes were being buffered in SQS, we took a MySQL dump and exported the data from the database into a flat file. So now that we have the flat file, what we did is we spun up our data import application and imported that data from the MySQL database dump into DynamoDB. Now remember, the packets, the writes to the database are still being buffered in SQS currently. And now that we have the data imported and have set the base for our new database, we start importing from SQS and replay the traffic that came in on the data center onto the new DynamoDB. Now, one really cool thing about this is, at this point, the DynamoDB is receiving the full production traffic, which means we can do our capacity planning without having any consumer impact. Because if it fails, we can just push the packet back into SQS and retry later. So for the actual rollout, we used a bridge and switch pattern, where the write traffic, you can see the two yellow lines at the bottom, it's write traffic and read traffic. And the traffic is still routed to the old application while replicating the data that is being written to the new application. So both applications are in sync. And then we can, because both applications are in sync, we can slowly start switching over read traffic from the old application to the new application. And we can validate what we build in AWS is exactly the same as we have it on-premise, and it still works as we expect it to. If anything should happen at any time, we can switch back the traffic from the new application to the old application and switch back without incurring any data loss or consumer impact, which was very important for us, because you don't want to lose your friends, obviously. So once we were confident in the application that we built on AWS and made sure it didn't have any bugs and stuff like that, what we did is we shut down the apps on-premise and waited for a few seconds for the Amazon SQS to clear its backlog. So to make sure that the last on-premise data status was replicated to DynamoDB, and then we flipped the write traffic over to the new app. And that's really all there was. At this point, the new application was running 100% in Amazon in AWS. So the next system I'll be going over is trophies. So since we have a lot of people who own PS4s or a PS device, I hope you're all familiar with trophies. It's the achievement system PSN. So you do something cool in a game, you get an achievement. You can compare it with your friends. It's kind of like showing off, stuff like that, right? I don't have many trophies. He has like super many trophies, so he's a little bit more invested in that. But it has a really simple data model because you have unlocked a trophy. It's a connection between you and the trophy. So however, what's really special about it is it has really strict data retention policies because, again, we don't want to lose your trophies. And if you get a trophy that you worked really hard for and you come back the next day and it's gone, you don't want this to happen. And also, we want data aggregation is required, so we calculate based on how many people played the game and stuff like that, how rare the trophy is. So again, I'm going to go over the original architecture, which again is a traditional data center. It looks very similar to Friends List if you look at it. It has an app server behind an L4 load balancer, database master-slave replication for trophies, and then it has the unlocked data, and we were running a cron job. every so-and-so minutes to do the calculation in the background, and it would actually flip some tables and really fancy stuff like that. However, again, with PS4 launch, we got a lot more traffic, and it was reaching the breaking point. So what we did, again, it looks super similar as to Friends, is we used Amazon to front load our caches in AWS. And again, it was super complex, and it had a lot of failure points, and the AWS cache can really only cache reads. It can't cache writes. So we decided enough is enough. We're going to put new architecture in place. It's going to be all cloud. It's going to be wonderful. We don't have to maintain it that much. And again, it's Amazon Route 53, an ELB, EC2 running the app service, and writing to DynamoDB and Elasticache. Now, if you remember, Trophy has a very unique aggregation requirements. So what we did is we utilized DynamoDB streams to kick off Lambda functions, which could then, on the fly, do those calculations and write those values back to DynamoDB and Elasticache. While also the AWS Lambda functions push the data into Amazon Kinesis Firehose, which then in turn stores it for us on S3 for later usage if we want to add a new calculation method. So let me go a little bit more into detail of the data aggregation. And it's a very similar approach to Friends, but the aggregation, as I already mentioned, it's a unique requirement for trophies. And we didn't want to use RDB systems due to scalability concerns. So we just moved off RDB systems due to scalability issues. So we didn't want to repeat that. And using DynamoDB streams and AWS Lambda to calculate those data was a really good option for us. So even though you see the line from Amazon Kinesis streams to S3 and then Amazon EMR, so actually during, I think, yesterday's keynote, they announced Amazon Athena, which we're super excited about because it might actually mean that we don't have to use Amazon EMR anymore. We can just go ahead and query that data that we buffered onto S3 and add new features super quickly. So lastly, a few challenges that we faced is data integrity, of course, is a requirement. So we actually spent multiple days, a lot more days than we thought, on reading back data from DynamoDB to ensure data integrity. So we would have use cases like, oh, let's write to the old app and read from the new app to make sure that it's working in production. Or read from the old app and read from the new app and compare that to make sure everything is in sync. Also, DynamoDB key names is one of our, the core developer for Friends found this, is, I think he's in the room maybe. If you're in the room, can you raise your hand? No? Oh, a little bit shy, but. So the key names in DynamoDB, we had really nice key names like user ID and stuff like that, name. But actually, once we reduced those key names to a single letter A, B, C, D, E, we reduced our cost by about 3 times. So you're paying for the key names as well, so just make sure that you don't pick super long fancy names because it's going to cost you. And last but not least, it's, so you've seen Alex and Dustin's session, hopefully. They were talking about active-active MultiRegion. We have similar requests, features that we would like to see. It's MultiRegion support for DynamoDB and MultiRegion support for RDS. TTL support for DynamoDB and also Redis cluster. It would just make our life so much easier. And I think that's about it. Thank you.